this class will be very important for competitive exams because in this class I will start talking about the ideals, mostly the prime ideal and maximal ideals. And in any question paper, for example in NET, GATE or NBHM, if you have a look at any question paper, you will certainly find 2 to 3 questions from this part. So from competitive exams, this part are very important. Not only that, in future when we'll talk about in your further course, when we will have the Galois field or the finite field construction, then you will certainly find that this prime ideals and maximal ideals, they play an important role. So today's class is very important in that way, not only from competitive exams viewpoint, but from abstract algebraic viewpoint. So that's why this class is quite important. So if you remember or if you read it from the book, I just told you a few references. You can read from any book. It's basically I plus j such that I belongs to I and j belongs to j. Okay. So if I and j are both ideals of a ring, then I plus j defined in this way is also, sorry, if I plus j are two ideals of a ring, then suddenly I plus j will also be an ideal of R. Let I and j be two ideals of a ring R. Let I dot j equal to I into j such that I belongs to I, j belongs to j. Is I dot j an ideal of R? So that is my question. So what is your opinion? Is if I define I dot j like this, then will that be an ideal? Okay, so that you should think whether this is true or false. What is your guess? Tell me, what is your guess?
The ideal.
That will be an ideal. So your answer is
Yes,
true.
sir.
So your
Because
answer is
I1,
true. So if it is your answer is true, then suppose let I1, I2 belongs to I and J1, J2 belongs to J. Then according to your definition, I1, J1 must be belongs to I into J and I2, J2 must be within I into J. Again, as I into J is an ideal of R, I1 J1 minus I2 J2 must also belongs to I into J. But how will you guarantee that this subtraction will also belongs to I into J? That is my question. Okay, so try to find. The answer will be false. So give some example this. Let us try to prove a result like R, say Rx quotient isomorphic to C. So in our last class, we talked about first isomorphism theorem. Can somebody be tell me how to prove this? Rx quotient x square plus 1 is isomorphic to Cx. So what we need to do? We need to have a mapping phi from Rx to C. How do I define this? So here this is a polynomial ring fx, and what should be where it should go? F of where it should go? where it should go? F of, any idea? So try to find what is your aim basically, what you want to prove. So if you want to use first isomorphism theorem, then what you need to do?
car of phi equal to generated by x square h.
R of phi should be equal to x square plus 1, right? Now this element, this polynomial must be from where? Must be from, this polynomial should belongs to where? From where I should take this? From which polynomial ring? Rx, right? Now tell me what should be this value? Okay, if I put f of I, can I be able to put f of I? What is I? I is the root of the polynomial x square plus 1 equal to 0. That means I square equal to minus 1. Okay. If I put this, can you prove that this phi is a homomorphism? Is it possible to for you to prove phi is a homomorphism? Can you prove this? Phi is a homomorphism. Okay. Let me ask you these questions one by one. Okay, Kailash.
Yes, sir. We take fx and gx from Rx,
Yes.
and phi of fx plus gx is equals to f plus gi.
Equal to, okay. Phi
Yep,
up. So you need to put actually not in that way. You should write it like you should take f plus gx.
yes.
That should be phi of fx plus. Okay, sorry. Yeah. So this should be equal to f plus g of I
Equal to
equal
fi
to
plus
fi plus gi. So equal to phi of f plus phi of fx plus phi of gx. Good. Then how to prove phi of f dot
f
gx?
equal to f dot gi equal to fi dot gi.
How will you prove that this is fi dot gi?
Because the operation is defined like this: f dot gi is equal to fi dot gi. When f dot gx is equal to fx dot gx, plus and dot are defined like this.
Plus and dot are defined like this. Okay.
Rx in
So
Rx.
in polynomial ring, okay, let me first check. So in polynomial ring, fx into gx is defined in how do you define this?
So fx we can expand the a0 plus a1x and b0 plus b1x.
Exactly. So then you can have this. So this is equal to phi of fx into phi of gx. That's good. Now,
Now we need to prove that it is onto.
so now we need to prove that this is onto. Very good. How will you prove?
So we need to
So
take any from C.
okay, let a plus ib belongs to c. Then what is phi of this equal to a plus ib? If you able to prove this, then you are done basically, right? Onto portion will be done. Then what will be your polynomial? Very easy.
Sir, A plus XB.
Very good. So this belongs to Rx and if you put I here, then it becomes this. That implies phi is onto. And then by first isomorphism theorem, we will have Rx quotient x square plus 1 is isomorphic to, since this is onto, this must, sorry, not, so it should be, it should write this quotient card of phi isomorphic to C. Now we need to show card of phi is equal to this. So we need to show car of phi equal to ideal generated by x square plus 1, right? Now I am sure that you know what do you mean by ideal generated by x square plus 1. What is the definition from my last class? So this is the ideal like this. This is an element generated by a single element. And since Rx is a commutative ring with 1, so how it should look like? It should look like some R into A, okay? Where this element R should come from the original ring. That means it should look like x square plus 1 into, I am putting this R element from the right because it's a commutative ring, it doesn't matter, some Gx such that Gx belongs to the ring Rx, right? So this is the definition. So here this is the definition. So this is the playing the role of the element R, and this is the playing the role of element A. So if you remember, if I just make a recall of this, so how should it look like? Since this is a commutative ring, the element should look like this commutative ring with 1 where R belongs to R. So you can write it also A into R such that R belongs to R. I am writing in that way. So this is my A. So this whole thing is my A, and this Gx is nothing but a polynomial because every element of the ring is nothing but a polynomial, right? So that's why this Rx belongs to, so this Gx belongs to this R. So the element looks like multiplication of x square plus 1 to any polynomial from Rx. Okay, now tell me how should we proceed? So what is actual the definition of car of phi? So what is car of phi? Car of phi means all such elements from the ring, say all such polynomials from the ring, say all such polynomials, say kx from the ring Rx, such that phi of kx equal to the zero element of the right hand side. What was there in the right hand side? It was C. So that means it's 0. That means all such kx belongs to Rx such that phi of this definition is k of I equal to 0. Good. So what is k of I? What does it mean? K of I equal to 0 means all such polynomial such that, so all such polynomial k x belongs to Rx such that ki equal to 0. What does it mean? That means I is a root of this polynomial, right? Then only I become ki would be 0. Now, can you tell me one polynomial from Rx such that I is a root? What is the simplest polynomial that you think about?
X square plus 1.
Very good, x square plus 1. But initially, you may think that x minus I or x plus I could be a solution. Say x minus I could be a solution, right? So if I consider fx equal to x minus I, then if I put x equal to I, then that becomes 0. That means fi equal to 0. But mind that this is not an element of Rx. So actually you cannot consider this polynomial as kx belongs to this. But to have the minimum degree polynomial, that is nothing but x square plus 1, then you see that this belongs to Rx and I is also a root of this polynomial. So all such polynomial such that you must have of this form into some gx such that gx belongs to Rx. Now, is this step clear to all of you? Because what you are finding, you are actually trying to find all polynomials which in which I is a root of that polynomial, right? But also you need to keep in your mind that that polynomial should also belongs to Rx. So it must be of this form, x square plus 1 into gx. Then you can understand that this is always 0 if you put I x equal to I, then this values is always 0. So the polynomial must look like this. Now what is this? This is nothing but the form of kx must be so such that kx equal to like this. It should be kx equal to this. So this is nothing but the ideal generated by x square plus 1. So finally what you have proved? You have proved that Rx quotient ideal generated by x square plus 1 is isomorphic to C, and that is very important result. In many of the competitive exams, you will find this result. Is the proof clear to all of you? Is the proof clear to all of you? Any question? If you have any question, all of you understand this? Okay. So let me again go to another very important result, which is the result related to another very important ring, C01. C01. This is nothing but, as I have already mentioned, all continuous functions from 01 to R such that f is a continuous function. Continuous function. So this we call it ring of all continuous functions, real valued continuous functions from 01 to R. And we have in our first class, we have already shown you that this is nothing but a ring. It's a commutative ring with 1. Okay. Okay. Now I want to prove an interesting result. Suppose, and in many of these question papers, you will find this problem or similar to this problem. Take any real number between 0 and 1, say half. So f belongs to C01 such that f of say half equal to 0. Okay. Now can you be able to tell me this is isomorphic to what? Can somebody be able to tell me this is isomorphic to what? So this question, this is isomorphic to what? Anybody? Anybody? Okay. Let's see. Shall we be able to prove that this is isomorphic to R? Let us try to prove this. Okay. So first thing, this has to be an ideal, right? So let us try to find, in our previous class, we have already seen that suppose I is f belongs to C01 such that f of half equal to 0. So of course, this is a subset of C01, no doubt about that. Now the question is I an ideal of C01? What will be your answer? The answer is yes. Of course, the zero mapping, that means everything from 0 1 it sends to 0, that is within this I. So I is non-empty, and you can check that if take any two elements f and g, then of course f minus g will also belongs to here. And take any element, any function from C01, and if you have say lambda belongs to C01, and what would be lambda of f evaluated at some point x. So uh, by definition, this is nothing but lambda x into fx, right? And since if you consider lambda f half, then suddenly it will be lambda half into f half, and it's given that f of value is 0, so this becomes 0. So lambda f will also belongs to I. As a result, I will become an ideal of C01. So this is very much I mean, you can always officially write like this because this is an ideal and this is a ring. So this is a commutative ring with 1 and this is an ideal, so you can always make a quotient. If I ask you to prove that, can you able to prove this, then again you will find it's not very easy or very direct proof you may not think of. But again, try to, wherever you will find this kind of quotient, always try to find this first isomorphism theorem helpful. First isomorphism theorem helpful. So let us try to use first isomorphism theorem to prove this. So what we need to prove a function from C01 to R. How will you define? Phi of some function f. And how will you define that function?
f of half.
Say f of half. Very good. Because see, you always try to make this as your kernel. And what is that kernel? The half value should be the zero element of this. See, it's already defined in that way. So now prove that. First try to check what you need to prove. First thing is that phi is a homomorphism. Then you need to prove phi is onto. How will you prove phi is onto? Can somebody? Homomorphism part is very easy, because you need to prove this phi is a ring homomorphism and it follows from the properties of f belongs to C01. It will be followed very easily. Now how to prove phi is onto? So you need to take any element, say a belongs to R. What you need to show? There exists some function f of which if you apply phi, that should be equal to your a. Can somebody be able to tell me what would be this f then? What would be your f? And that will justify your answer. Anybody?
So 2ax.
2ax. Okay, let's see. Fx equal to 2ax, right? Now if we apply phi of f, then it should be f of half, and that is equal to 2a into half, that is equal to a. That means for a belongs to R, there exists this polynomial fx. So suddenly this is a continuous mapping. Is it a continuous mapping? Is this a continuous mapping? So this is a polynomial, so it has to be a continuous mapping. So this belongs to C01 such that phi of f equal to a. That's very good. You can also make some constant function f that every value goes to A. That would also be possible because a constant mapping is also a polynomial, and hence it's a constant, it's a continuous mapping. So again, this is also good. So you find that for this A, there exists some function fx, which is a continuous function from 0, 1 to r, such that phi of f equal to A. So what would be your conclusion? That implies phi is onto. Then by first isomorphism theorem, you are now almost done. Then by first isomorphism theorem, we have C01 quotient kernel of phi should be isomorphic to your R. Now what is car of phi? Now car of phi should be all such function from C01 such that phi of f must be equal to the zero element of the right hand side, equal to 0. That means all such function f belongs to C01 such that phi of f, that means f of half, equal to 0. Now just have a look at your problem, what I have given. So it was like the same thing, exactly the same thing. That means my I. So this is nothing but my I. So we have proved that C01 quotient I is isomorphic to R. So that's very interesting. But in a direct way, if you are going to prove this, it's of course possible to prove that you can have a direct mapping from this quotient to R, and then you can define this. That could be done. But this is a very simple technique through which you can apply and you can solve many of such difficult problems that usually they are asked very frequently in the exam. Now you can understand that there is nothing special about half. So you can very well replace half by any real number between 0 and 1. So you can always prove that C01 quotient, all such polynomial belongs to C01 such that f of, maybe you can write it d, there are a lot of c's are here, so I'll replace c by d, f of d equal to 0. That is also isomorphic to R. So you can understand, instead of half, you just need to replace half by d and your proof is ready. So it's very simple. So there is nothing special, but certainly I will in details in my subsequent classes, I will also deal with much details with this C01, where we will show that many other properties of C01. And if your if your topology, if you are have some knowledge on topology, then I will show that you can replace this by many other topological, arbitrary topological spaces. I'm sure by now on you might have heard about the compact subset of topological spaces, and then you know that what is T2, T1, etc. So depending on these properties, we can replace C, then our function will be, our ring will be Cx. That means X will be some maybe compact T2, compact T2, and so on. So that we will show, and depending on that, we'll have some extra more properties that we will able to generalize the whole result. But that will require a whole class. So in my subsequent classes, I will certainly pay more attention on C01, because from exams viewpoint, C01 plays an important role. So till now, whatever I taught, I think it's clear to all of you. Is it any question or comments? If you have, please ask me. If you have any question or comments, you can ask me. Okay. So next, what we are going to show is some specific properties of ideals. And the special properties of these ideals are known as prime ideals and maximal ideals. Okay. So before going for the much details, let us first have try to have some kind of motivation. So usually when we talk about prime numbers, so prime numbers, So if I ask you this question, can somebody tell me what is a prime number? In your number theory classes, you might have all done this definition from your, maybe from your school level, you know this, what is a prime number. So can somebody tell me what is a prime number? Somebody? Somebody from the class, can you please tell me what is a prime number? Somebody? Okay. Let me, Provitro, are you here?
Yes, sir.
Okay. Can you please tell me what is a prime number?
Prime number is a number which is divisible by only one, and that the number p.
Okay. So whatever you are telling, I'm writing. So prime number is a number which is divisible by, can you please repeat once again, which is divisible by?
One and the number itself.
And the number itself. Okay. So if this is your statement, so will anybody negate this, or anybody wants to add something to it? Anybody, please come forward. Is the statement correct?
So that is only by only.
Divisible by only. Okay, only divisible by only. Okay, only one and the number itself. Anything else you want to add? Anybody? Okay, so prime number is a number which is divisible by only one and the number itself. Okay, this is your definition. Now tell me, is,
So first of all, prime number is natural number.
okay, I assume that this is means a natural number. Okay, you added this idea, natural number. Okay, natural number means it should be greater than equal to 0, right? Okay, then is this addition or anything else you want to add?
Greater than 1.
Okay, so the second addition is he added just a natural number. Now it's a greater than 1. See how many modifications are there. Let's see. Okay, then anybody else? Anybody else want to add something more? Okay, now tell me, if this is your final answer, is 5 a prime number? Is 5 a prime number? So if prime 5 is greater than 1, and 1 and 5 are the only divisors according to your definition, right? My question is minus 1 a divisor of 5? Is minus 1 a divisor of 5? True or false? True or false? What would be your answer? Tell me quickly. Minus 1 divide 5 or not? What is your answer? True or false? Minus 1 divide 5 or not? Does minus 1 divide 5 or not? So of course, minus 1 certainly divides 5, right? So 1, minus 1 and itself, even minus 5 also divides 5. So there is a confusion.
So positive divisor.
Okay, now you have added, so divisible by only 1 and the number itself. So and the number itself are the only positive divisor, right? So now I can state in a fresh way. So what is prime number then? prime number. So a positive integer greater than 1 is said to be a prime number, to be a prime number if 1 and that number are the only two positive divisors of that number. Okay, so a positive integer, it has to be greater than 1, is said to be a prime number if 1 and that number are the only two positive divisors of that number. Now you can understand that 5 is a prime because 5 is greater than 1, and 1 and 5 are the two, exactly the two positive divisors of 5. That's why. So that's what my question, I mean, that what I want to point out. We know the definition, we can find the examples clearly, but when the formalism comes, because that's the way of writing, the formal writing. So when we are going to write something in a formal way, sometimes we miss something. So at our back mind, or back of our mind, all the things are there, but when we express ourselves formally, sometimes we miss out with few of the points, and that's not really good for the interview. So those who will be facing interview for their future career and all, there you have to be very specific, and these are the points where you should keep in your mind, that whatever you are going to define, you need to justify, to check whether it really fulfills all the properties that you want to say or not. Okay, so that's a important issue. Now this viewing at, as I mentioned in my earlier classes, that z plus dot is basically one of the basic motivations for the advancement of ring theory. So many properties of rings are being studied just by seeing the properties of z. So in Z, mostly in natural number, we have the properties of prime numbers. So similar elements, similar things can we have in Z? Because in Z we also have negative integers, but prime numbers are basically for prime for natural numbers. So can we generalize this concept of prime numbers in case of Z? For example, can we have the similar thing for -5 as well? So -5 will certainly not an prime number, but can we generalize the similar concept here also? So then the idea of prime element came into picture. Prime element. So as you understand that it is not an number, it's an element. So you can then very well replace Z by any arbitrary ring. So in case of any arbitrary ring, can we have the concept of prime element? So prime element in an arbitrary ring, which actually generalizes the concepts of prime numbers that we have usually defined in the set of natural numbers. So the same flavor should be propagated to the arbitrary ring. So that was the kind of arbitrariness that we should introduce over Z, because within Z we have a fixed kind of the numbers, very beautiful properties of rings are there. But can we generalize for arbitrary ring? And then when we started thinking about that, then few things came up. The one of the most important topics of this algebra is prime ideals. Okay, see, in case of prime numbers, why they are very important? Because of fundamental theorem of arithmetic. That's why, so you can say that these prime numbers are the building blocks of integers. So fundamental theorem of arithmetic. What it says? It says that if you consider any integer which is greater than equal to 2, then suddenly you can write that integer as a product of primes. And that representation is unique with respect to some kind of permutation of these primes and all. So that we all know. That means what it essentially says is that any natural number is basically built up of many prime numbers. That means if we are able to study the prime numbers properly, then basically we may have lot of information about n itself. That means like our buildings, like the cement and the sands, they are the building blocks of any building. Here also for numbers, for integers, these prime numbers are considered to be the building blocks. Likewise, in case of ideals or in case of rings, this prime ideals, I will show later on that these prime ideals are considered to be the building blocks of some rings, and that will be explained through some examples and through theorems. But before proving that, let us try to have some basic idea about what is a prime ideal. Okay, and mind that we are not within the ring of integers and all. Now we are within the domain of some arbitrary ring. So first we are going to define what do we mean by prime ideals. Note that, so this prime ideal, this definition can be done over any arbitrary ring. The general definition for prime ideals is basically over any arbitrary ring. But in my classes, for the sake of simplicity, we assume that the ring is a commutative ring with 1. So let us assume that our ring is a commutative ring with 1. 1 means identity element of 1. Mind that, note that, we must note that prime ideals can be defined over arbitrary ring. But for the sake of simplicity, we are assuming that R is a commutative ring with 1. If R is not a commutative ring with 1, the definition will be in the definition that is given for prime ideals in a general setup. But if we assume that the nice property that the ring is a commutative ring with 1, then the definition is very simple. And for most of the competitive exam problems, we actually assume that the ring is a commutative ring with 1. Usually that are asked for. Okay, so what is this prime ideal? So again, I am assuming that let R be a commutative ring with 1. A proper ideal, mind that a proper ideal, that means properly contained in R, is said to be a prime ideal of R if for all AB belongs to R, A dot B belongs to P implies either A belongs to P or B belongs to P. See, let us first try to have a background why this is a kind of definition. So when we call a prime integer prime integer p divides ab. What is the implication of it? Either p divides a or p divides b. If p is a prime integer, then if p divides ab, then that implies either p divides a or p divides b. Okay. So what is the meaning of a division here? Okay, let me first go back to the definition of prime ideal. First important part is this ideal has to be a proper ideal. That means if we consider, why we consider this is proper ideal, I will coming to that, but it has to be a proper ideal, is said to be a prime ideal of R if for all AB belongs to R, A into B, if that belongs to P, implies either A belongs to P or B belongs to P. Now, why we are considering this to be a proper ideal? If this is not a proper ideal, for example, if we consider this P to be, let me see, a proper ideal P. So name it P. A proper ideal P is said to be a prime ideal of R if for all AB belongs to R, A dot B belongs to P implies either. Now, if I consider this P to be R, then you can understand that this definition will always hold in case of R. A dot B belongs to R implies either A belongs to R or B belongs to R. So there is nothing special if we consider P to be R. That's why in the definition of prime ideals, we must assume that P is a proper ideal. That means which is properly contained in R. Okay. So let us try to find some example. Suppose my R is Z and my P is say 3Z. So question is 3Z a prime ideal of Z? Let us try to check. First, Z is a commutative ring with 1. Now what we need to check, take any two elements belongs to Z such that A dot B is belongs to 3Z. What we need to show? We need to show either A belongs to 3Z or B belongs to 3Z. That implies 3 divides AB because A into B is within 3Z. That means within the within the set which is nothing but consist of all multiples of 3. And now 3 is a prime integer. Now we are within the domain of the natural numbers, or we can think of 3 as a prime integer. That implies either 3 divides A or 3 divides B. And that means either A belongs to 3Z or B belongs to 3Z. As a result, 3Z is a prime ideal of Z. Now, if I ask you the same question, is question is 4Z a prime ideal of Z? What would be your answer? True or false? Somebody, let's see whom to ask. Nikita,
False.
is why false?
If
Why false?
if we take AB belongs to 4Z,
AB equal to 4Z or 4?
hmm,
4. So if you
4,
take 4, 4 equal to 2 into 2 belongs to 4Z, but 2 does not belongs to 4Z. Very good. Okay. So if this is a prime ideal, then either this will belongs to this or this will belongs to this. That means 2 must be belongs to 4Z, but 2 is not in the 4Z. That means this result is false. Okay. So is 0 ideal a prime ideal of Z? True or false? Somebody, let's see over there. Okay. Sariful, is zero ideal a prime ideal or not?
So maybe if R is a ID, then zero ideal is a prime ideal.
No, no, I have given Z, right? I have given already
Hmm.
Z. Now, what is your conclusion?
Yes, zero ideal is a prime ideal.
Okay, true. Because if we consider any two elements belongs to Z such that A dot B belongs to the zero ideal, what does it mean? That will mean A dot B equal to 0. And as he says that Z is an integral domain, that means either A belongs to 0 or B belongs to 0, since Z is an integral domain. So is the question, next question, is zero ideal is zero ideal always be prime ideal in any ring? If you consider zero ideal of any ring, will that be always a prime ideal of that ring? What will be your answer?
No, sir.
Example.
Z by 6Z.
Very good. So in 6Z, if we consider in 6Z the ideal zero ideal, in case of class 2 into class 3, this equal to class 0, this belongs to Z6. So in our last class we have seen that Z quotient 6Z is isomorphic to Z6, but none of 2 or 3, that does not belongs to Z6. So zero ideal may not be a prime ideal in arbitrary ring. But of course, as you understand, if the ring is an integral domain, then certainly zero ideal is always an prime ideal. So zero ideal is a prime ideal in an integral domain, and that is true. And that is true. Okay, so there are few interesting facts that we should take care about, and many times in many forms this kind of questions are being asked for competitive exams. Okay, now let us try to find. Okay, say in Z6, can you give me a prime ideal? In Z6, can you give me a prime ideal? First of all, 0 is not a prime ideal here. You cannot consider Z6 to be a prime ideal, because for prime ideal it has to be strictly contained within Z6. So you cannot have also this. Now can you give me any prime ideal within Z6? Anybody?
Z6 has no prime ideal.
Okay, so your claim, you say that Z6 has no prime ideal. Why do you think so? What is your justification? Okay, let us try to consider this 0 a set. I'm not saying that this is an ideal. Okay, I'm saying that consider this set. So this is certainly a subset of Z6. Question: is I an ideal of Z6? What is your conclusion? Is I an ideal of Z6? is a non-empty subset. If you take any two elements from here, if you subtract them, that will also be within Z6. And take any elements, for example 0, 1, 2. If you make it 2, then this becomes 0, this becomes also 0, that is within 6, Z6. If you consider 3, that then becomes 9 within 6. If you consider 4, 12, that becomes 0. If you consider 5, that becomes 15, and that becomes 3. So what would be your conclusion? True or false? True or false?
True.
So this is true. That means get 6. Now my question is so this is wrong. Okay, so this is an ideal, not yet wrong. Is I a prime ideal of Z6? What will be your answer? Okay, so take any two elements. Say AB belongs to Z6. Say AB belongs to Z3. Z6. So what you need to show? You need to show that either A belongs to Z6 or sorry, A belongs to so A dot B belongs to not Z6, A dot B belongs to I. So what do you need to show? To show either this belongs to I or this belongs to I. So what is your guess?
Yes, it is a prime ideal.
So this is a prime ideal. So after few steps, you will able to conclude that I is a prime ideal of Z6. I will give you a result which actually will help you to prove that this will be a prime ideal. But before that, I will do some more things, and then it will be clear to you. Now you can understand that Z6 within Z6 we will always have a prime ideal. Now if I consider F to be a field, suppose F is my field. Okay, question. Let F be a field. Then can F contain a prime ideal? What will be your answer? Yes or no? Say any field. Can first of all, uh, for field, it's very easy to think because how many ideals are there in a field?
Only two, 0 and the whole field.
Very good. 0 and the whole fields are the only two ideals of the field. Now
0
you
is
cannot, yes, you cannot think about F because F is not properly contained within F. So only thing is the 0 ideal. Is 0 ideal a prime ideal of the field or not? Tell me.
yes, because field is an integral.
Yes, just now we have mentioned one result. If this is an integral domain, then 0 ideal is a prime ideal. So suddenly the answer will be yes, and the answer is 0 is the only prime ideal. Only prime ideal. Okay. So now you have basic ideas of what are prime ideals and how they look like. Okay. Now I will describe few of the properties of prime ideals. Okay. So, in my last class, I mentioned about ideal generated by a single element. We call this ideal as principal ideal. Principal ideal. Now, if an integral domain in which every ideal is a principal ideal, then we call that integral domain as, what is your the name that you must suggest? Can somebody be tell me what could be the name that you must suggest that it should satisfy this property? So every ideal in that integral domain is a principal ideal. Then what should be the name that you suggest to it? What should
Principal
be
ideal,
the
principal
prin-
ideal domain.
very good. So it's known as principal ideal domain. And in short, we call it PID. So this PID plays an important role in your maybe the next semester, in your third semester, on maybe in the fourth semester, we'll also have the ideas in over PID and the modules over PID, and that gives a very good relation between the canonical, Jordan canonical form and all. That will also teach you during your further courses when you will be in at your higher level of your studies. So that's why PID plays a very important role in your next few classes. You will find that PIDs are basically playing an important role here. Okay, so the first thing, a theorem, you can say that a theorem, let R be a PID, R be a PID, and P not equal to R be a proper ideal of R, such that P not equal to the zero ideal. Then P is a prime ideal of R if and only if P equal to this, that is P is generated by a prime element of R. So just now I mentioned about prime ideas. So now I need to mention about what do you mean by prime element. That means what it says that if you consider a non-zero proper ideal of R, and that ideal is a prime ideal, it's very important if and only if this ideal is generated by a prime element. That means what you need to prove that this is a prime element. So if you assume that P is a prime ideal in a PID, then mind that this is very important. Zero is not included. Why it's not included? I will come to it. So what it says that if P is a prime ideal, then this prime ideal must be generated by a prime element. And conversely, if P is an ideal which is generated by a prime element, then it has to be a prime ideal. So the prime question that comes to our mind is, what is a prime element? So the definition I have not yet defined. So what is a prime element? I have given you the intuitive idea, but not the exact formal definition. Again, for the sake of simplicity, I assume that let R be a commutative ring with 1, then a non-zero, non-unit element P belongs to R is said to be be a prime element of R if for all AB belongs to R such that P divides AB implies either P divides A or P divides P. The same definition as we follow for the prime numbers. See, P divides AB implies either P divides A or P divides B. Now the question that, first of all, these terms are very important: non-zero and non-unit. So you for a prime element you cannot have an unit element, that means whose multiplicative inverse exists. You cannot have an element. For example, 1 can never be a prime element. Similarly, 0 can never be a prime element. That's why they are the generalization of prime elements. So in case of a prime numbers, as you've seen that the prime numbers should be greater than 1, that means you cannot have 0 or 1, right? And if you consider this, then that will actually, non-zero means you have already taken care of 0, and non-unit means you have already taken care of 1. So you cannot have both of them. Okay. So what is then this prime element? That's why this is not a prime number. I call it prime element. And what is the meaning of something divides something in a ring? That means what is the meaning of A divides B in R? That means there exists some C belongs to R such that B equal to AC. Same as 3 divides 6 in Z. What does it mean? That means there exists 2 belongs to Z such that 6 equal to your 3 into 2. See, the same thing. The same way we define also in case of any arbitrary ring. Now all the notations are clear to you. So example, if I consider Z, then you understand that 3 is a prime element. Also minus 3 is also a prime element, which was not there in case of a prime number. But now if I consider minus 3, then that is also belongs to Z, and that also satisfies these properties. So minus 3 is also now my prime element. So now you can extend this whole definition in case of any arbitrary ring. But as I mentioned, for the sake of simplicity, I have taken the ring to be commutative ring with 1. Okay. Now, if I ask you this question, is class 3 a prime element in Z6 plus dot? What will be your answer? Yes or no? Yes or no? Is class 3 a prime element in Z6 or no? Okay, so that will be your question. Note that you may not be able to answer this question from here because it says that a prime element. So we have already seen that in Z6 this ideal 0 and 3 is a prime ideal. So I have given you the task to check whether this is prime or not. Prime or not, right? That is my question. So of course, this result states that this is a prime ideal if and only if this is generated by a prime element. So you can understand that very well this is generated by class 3. But still you cannot use this result. Can you somebody be tell me why you cannot use this result to conclude that class 3 is a prime element? Can somebody tell me why? So here, see, here everything is there. So this is generated by a prime element. I mean, generated by not a prime element. This is a prime ideal. So this is a prime ideal if and only if this is generated by a prime element. The result saying that. But still, in Z6, you cannot use this. So this is generated by 3. This is a prime ideal. But whether you will be able to tell that 3 is a prime element in this, can you tell me whether 3 is a prime element using the above result? That is more important. Can you use this above result to prove that? Somebody?
Z6 should be PID
Very good.
first of all.
So Z6 is not an integral domain. So you cannot use this result. It may happen that class 3 is a prime element in Z6. It may happen or may not happen, but still you cannot use this result to give your answer. Okay. Okay, so I'm just giving you a kind of homework to check whether class 3 is a prime element or not in Z6. Any quick answer? Can somebody be tell me whether it's yes or no? What would be your answer? Is class 3 a prime element or not in Z6? Quick answer, very quick. If you are taking some time, then it's better you do it at your home. But what I want to mention that you cannot use this result to give your answer, because it's the result is only true for PID. It's not for any arbitrary commutative ring with 1. Okay, now let us try to prove this result. Okay, so how will you prove this? Any guess? So what you need to prove, have a look at this. First, you assume that P is a prime ideal. Since this is a PID, so all the ideals will be generated by some single element. So that will be generated by some single element P. What you need to show that P is a prime element. That's all. Then you are basically done. So proof technique is very simple. So proof of this result. So assume that. So let P be a prime ideal of R, as R is a PID. P must be generated by some single element, right? Okay, what is given? Since P is what, two more things are there. See, in the statement I have already given P is not equal to 0 and P is a prime ideal. So as P is not equal to 0, what can you tell about P? Small p? P can never be 0. So if P is a 0 element, then you cannot get a non-zero ideal, right? If you generate by 0, then all the ideas that will be generated by 0 will be 0 ideal itself. But P is given is a non-zero ideal. That's why P is non-zero. Now, in the definition of prime element, so what is your aim? Our aim is to show, our aim is to show P is a prime element of R. So if I go back to the definition of prime element, what it says, commutative ring with 1 is already done. A non-zero, I have already seen this is non-zero, and I need to prove that this is also a non-unit element, then satisfying these properties. Okay, then I need to show these properties are satisfied. But first thing, we need to check whether this P is an unit or not. So what happens if P is an unit? Claim P is non-unit. Why so? Why this claim is there? Can somebody be tell me why P is non-unit? What will happen if P becomes unit?
So if P is
Then
unit, then one in
one will belong to the ideal.
Very
Then
good.
ideal will be
Yes.
the full R.
So very good. If P is a unit, then the ideal generated by will be equal to R, a contradiction. As our hypothesis says that R not equal to P, equal to ideal generated by P. So it can never be happening. So what is your then first steps are done. So P is non-zero and non-unit. That part is done. So what you need to prove further? You need to prove that let AB belongs to R such that P divides AB. What you need to show? Either P divides A or P divides B, right? Now tell me, now have a go back to the definition of prime. Till now I haven't used this. This is a prime ideal. What we have shown all the properties of P and all, right? So primeness is being used here. So let AB belongs to R such that P divides AB. What does it mean? That means AB must belongs to the ideal generated by P. Is the is this statement clear to all of you? This will be very frequently is used this kind of concepts. Is this statement clear to you? Why so? Because P divides AB. If I go back to in detail, P divides AB. Just now we have mentioned P divides AB means there exists some say C belongs to R such that AB must be equal to C into P. Now P is a PID. So every element of this should look like some X into P or some R into P. So here this looks like R into P type. So what does it mean? That means this belongs to ideal generated by P. That's why I have written this belongs to P. Is the step clear? So this kind of step will be very frequently used in all the arguments that are usually used in case of prime ideals and all. So that means this equal to actually P, capital P. Now what is given? The definition of prime ideal we need to check. What is the definition of a prime ideal? The definition of prime ideal says that, where is it? Maybe at here somewhere. So if you remember, yes. So here, if you remember, what is the definition of prime ideal for a commutative ring with 1? Is said to be prime ideal if for all AB belongs to R, A into B belongs to P implies either A belongs to P or B belongs to P. That's what we are going to use here. So you have till now you have shown that AB belongs to P as P is a prime ideal of R, either A belongs to P or B belongs to P. What does it mean? That means either, again just the opposite direction, I am using the same argument, either P divides A or P divides B. That means P is a prime element of R. So what we have started with? We started with a prime ideal, and we have shown that that ideal is generated by some element P, and after few arguments we finally able to prove that this element P is nothing but a prime element of R. So this part is done. One part is done. Next, what we need to prove? We need to prove that if in a PID, if some non-zero ideal is generated by some element P, that means given that, so conversely, let the ideal, let P equal to ideal generated by P, where P is a prime element. Then what do we need to show? We need to show, then we need to prove P is a prime ideal of R. So how to prove that? The proof technique is very easy. So let AB belongs to R such that A into B belongs to P, and that is nothing but this. That means, what does it mean? From the same argument here, that means P divides AB. Now P is a prime element. What is the definition? From definition, that means either P divides A or P divides B. That means either A belongs to P or B belongs to P. That implies P is a prime ideal. Now I missed one point. Can you please identify that? To prove prime ideal, I missed one thing. Can you identify that? See, P is a prime element. So P is basically generated by some non-zero non-unit element. So if this is generated by some non-zero and non-unit element, then suddenly P cannot be equal to the whole R, or P cannot be equal to the zero ideal, what was given at our hypothesis. So basically we are done, right? So what we have proved is that if we start with some prime ideal, then that prime ideal has to be the ideal generated by some prime element, and that happens if and only if result only if we are within a PID, and that prime ideal or should not be a zero ideal, or the prime ideal, as I mentioned, it cannot be the whole ring R. Is it clear to all of you? Now I just mentioned few of the results that will be very much helpful for all the competitive exams. Okay, let me save this. Uh, Today is 12 to 21 ring. Okay, have some new. So here uh, we were going to give some extra results that will be very much useful for all the problem solving statement. Now, if I my question, okay, okay. So my question is, give me all prime ideals of Z. Can you give me all prime ideals of Z? Who are the all prime ideals of Z? Tell me, somebody.
Sir, PZ where P is prime.
Okay, somebody says PZ
Where P is prime.
P is prime. Okay, remember that I want all prime ideals. Are they all prime ideals of Z? Any addition, alteration you want? Anything else?
Zero
Most of,
ideal.
yes, most of the students they miss this along with this zero ideals. It has to be considered because Z is a PID, and in this ideal, zero ideal is a ideal. That's why now you can understand, that's why I have missed this P should not be equal to zero ideal in my last statement. In the theorem that I have proved, there we assume that P should not be equal to zero. But here you can understand that if I consider all prime ideals of Z, that must be of this form. Pz where P is prime along with the zero ideal. Many of the students they miss this point. As a result, they lose maybe 4.75 or 3 points in the exam of NET exam. Many years. So this is very common question for many years. Okay. Now let me give you another type of ideals which is known as maximal ideal. That is also very important, maximal ideal. So from the name you can understand that what does it mean, what is the meaning of a maximal ideal. That means suppose we have some ring R and I is an ideal. When we call I is a maximal ideal, that means you cannot find any ideal J which is properly contained in between, which lies strictly between this and this. When this kind of scenario happens, we call I to be a maximal ideal. So again, I will consider this in case of this commutative ring with 1. So let R be a commutative ring with 1. Then a proper ideal. Mind that proper is important. Proper ideal, say M, is said to be a maximal ideal of R if there exists no ideal J of R such that I is properly contained in J and that J is properly contained in the ring R. That means if you cannot have an existence of some ideal which is strictly bigger than n and which is strictly less than R, in that sense we call it maximal and not maximum. Why not maximum? For example, if we consider this to be Z plus dot, then you can give the idea of 2Z. So you cannot have any ideal which is strictly between 2Z and which is strictly less than 3Z. Sorry, Z. Again, you can understand that if I have 3Z here, there must be some intersection which consists of 6Z. So again, strictly bigger than 3Z and strictly less than Z, there is no such ideal. So both 2Z and 3Z are maximal ideals of R of Z. Okay. So that's why you cannot say that who is bigger, 2Z is bigger or 3Z is bigger. So you cannot compare them. That's why we call it maximal and not maximum. For any such rings. So maximal and prime ideas, they do have lots of common features and they might have some connection in case of a commutative ring with 1. Okay. Uh, First, I am just giving you first few results that you need to read from the book, any book. You can have a look at my book or Malik Sen Morrison or Damit Food. So what is that result? So let R be commutative ring with 1. Then every maximal ideal of R is a prime ideal. If the ring is a commutative ring with 1, remember, if you have any maximal ideal, then it has to be a prime ideal of R. So that is a very interesting result, and these proofs are very easy to prove. Now the question is the converse true? That means in a commutative ring, is the converse true? Question, is the converse true? So what I tell you, need to prove these results from any book. So you need to prove this. So take home. Okay. Now my question is the converse true? What will be your answer? True or false? What will be your answer? True or false? Okay, what will be your answer? True or false? What is your answer? True or false? Somebody?
False.
Okay. So somebody says it's false. Why?
In case of Z,
Yes.
uh, every maximum ideal is not prime ideal.
In case of Z, every maximal ideal is not prime.
Sorry. Sorry. Every prime ideal is not maximal.
Yes. Why? Very good.
Uh, zero
Yes.
zero ideal
Yes. So 0 is a prime
prime
ideal,
but not maximal
prime
also.
ideal, but not maximal. You can understand many ideals are there which are strictly bigger than this ideal, not a max ideal of set. Very good. So, is the question is then when we will call that this ideal maximal implies prime as well as prime implies maximal, that we need to check. So that is, it says that for a in a PID, let R be a PID, let R be a PID. You understand what is the meaning of PID? Means principal ideal domain. Then a non-zero ideal P, of course P should not be equal to R, of R is prime if and only if it is maximal. See, in a PID, mind that this is very important. That's why you need to remember the example of Z. So a non-zero ideal P is prime if and only if it is maximal. So one part is done. So since this is a PID, then it must be a commutative ring with 1. So if this is a commutative ring, every maximal ideal is prime. That part is done. But what we need to prove, every non-zero prime ideal has to be a maximal ideal in PID. So this part is also take home. So you can read my book from where you will get this, or from Damit Food or from Malik Sen Moderation. Now I'm going to give you another very important result, which will also be a take home. It gives you a relation between this integral domain prime ideal and then field and maximal ideal. It says that let R be a commutative ring with 1 and P an ideal of R such that P not equal to R. That means a proper ideal of R. Then P is prime if and only if R quotient P is an integral domain. It's a very important result and very easy to prove. But this result does have a lot of applications in, you will find that in your competitive exam, this kind of questions are very frequently asked, and this results plays an important role. So since this is a quotient from, sometimes these results are also involved with first isomorphism theorem, and by first isomorphism theorem you may go to some known integral domain, and from there you have to give your answer. So this result is also very important. Another result, so here this relation is among this prime ideal and integral domain. The similar result is also there for and maximal ideal and field. So this says that let R be a commutative ring, the same result. R be a commutative ring with 1 and M be an ideal of R such that M not equal to R. That means a proper ideal of R. Then M is maximal ideal of R if and only if R quotient M is what should be my result? It should be a, fill in the blanks, please say somebody. It should be a, somebody please try.
Field.
field,
Yes, very good. It should be a field. And this result is also very easy to understand. The proof is very easy. I'm not going to the proof of this because we don't have much time. But instead, what I will go for few of the very recent problems that comes in the exam of NET exam. So I think that would be easier for you to understand. And another result, I'm just going to give you the result. Uh, this result sometimes are very important. The proof requires the Jones lemma. So I'm stating you this result. It says the result looks very simple, but to prove it for the existential part, you need Jones lemma. Okay, I'm not going to give you the proof. Let R be a commutative ring with 1, then any proper ideal of R is contained in a maximal ideal of R. Let R be a commutative ring with 1, then any proper ideal of R is contained in a maximal ideal of R. The result is very easy to state, but it requires little bit theoretical things to prove it, and it requires the properties of this Jones lemma and all. So I'm not going to give you this proof here. So it's also a take home. If somebody will have some problem, please let me know. I will make it clear too. It's not very difficult, but step by step things has to be done. What it says, if you consider any commutative ring with 1, say R, and if you take any proper ideal, say I, then you can always find a maximal ideal M such that I is contained in M. Okay, that means every proper ideal is contained in a maximal ideal. Take any ideal, it may be a maximal ideal itself, then I is contained in I itself because I is a maximal ideal. If I is not a maximal ideal, then you will suddenly find an ideal M which is a maximal ideal of R such that I is contained in M. So that's very important result, and sometimes these results are being asked in some of the questions. Okay, so let me first try to find some of the problems that are usually very important from NET viewpoint. Yeah, so this problem came in 2019 December. You can see this screen, and you may take a screenshot of it. So it came in December 2019 NET. So C01, you all know now what is the meaning of C01. So A is a we have shown that for any c, we did it for half, and you can take it for 2 by 3 by 4 as well. Then of course a is an ideal, no doubt about this. Now tell me what would be the answer. It should be a multiple correct choice. More than one could be your correct options. Okay, tell me this.
It is a maximal ideal.
Okay, maybe more than one it could be the answer. It would be a maximal ideal. That means which one is 3 is correct. Anything
It is
else?
also a prime ideal. Also a prime ideal.
It's also a prime ideal. Why it is a maximal ideal? First of all, tell me why it is a maximal ideal.
Because we have seen previously that C01 quotient A isomorphic to R, and R is a field.
Exactly, exactly. Just now we have started this result. Okay, this result. We have seen this. So what we have seen that in our previous, at the beginning I started with this kind of problem, all such f belongs to C01 such that f of 3 by 4. There is no extra meaning of 3 by 4. It could be any c between 0 and 1, this 0. And that was isomorphic to, we have stated that this is isomorphic to r plus dot. And this is a field. And if this is a field, this is a commutative ring with 1. This is a field. And what this result states? It states that M is a maximal ideal. That means this is a maximal ideal. So this is a maximal ideal, right? So go back to the options. So this option is correct. M is a maximal ideal. 3 is correct. Okay. Now tell me what's about this is an ideal but not a prime ideal. But what next? Is it a prime ideal also? Is
Yes, sir.
this this is a
Yes,
prime
yes.
ideal because of this result? In a commutative ring, we have seen that every maximal ideal is a prime ideal, right? uh, have I mentioned it? Yes, I think I have mentioned it. In a commutative ring, every maximal ideal is a prime ideal. So it just now we have seen that this is a maximal ideal. As a result, this is within a commutative ring with 1, so this must be a prime ideal. So this is also correct. So 2 is also correct. Now is it this prime ideal but not a maximal? Is this correct? This is not correct, right? So it's a prime ideal but not a maximal ideal. So we have seen that this is both prime ideal as well as maximal ideal. So option 2 and 3 will be the correct option, right? Okay. So is it clear to all of you? Good. Now let me go to this point. Uh, yes. Okay. Let's check. Let R be a commutative ring with 1. Which of the following is true? Again, multiple correct choice. Maybe it came in 2019 June. If R has finitely many prime ideals, then R is a field. Is it correct? If R has finitely many prime ideals, then R is a field.
Sir, a field has only two ideals, and only the
Yes.
zero ideal is prime. So it is mm, it is trivially correct.
But it is the statement saying this? If
No, no, no.
R has a finitely many prime ideals, then R is a field. What you are telling other way around. If it is a field, it might have must have finitely many. But it has given you the other way around. Okay, let's see. Two. If
It
R
cannot be.
has,
It
sorry,
cannot be.
for example,
Example. Sir, Z6, if I take
Z8. Z8.
yes, yes, Z6 or Z8. So in
this,
Z6, we have already seen that this is a prime ideal, right? We have already checked. This is a prime ideal. So we understand that since this is a finite ring, so it must have finitely many prime ideals. but this is not a field. Similarly for Z8 as well. Okay, so it has finally many, so it is not correct. Is the second is correct? If R is finally many ideas, then R is finite.
No, sir.
No.
M to R.
Example?
M to
Any
R.
rationals or
Sorry.
real numbers?
Yes, so any infinite field will do here, right? For any infinite field, you can see that there exist exactly two ideas, zero ideas, and the ring itself, but it cannot be finite because it's an infinite ring or infinite field. So R, Q, C, anything. Okay, this one may be a little difficult for you. Uh, if R is a PID, then every subring of R with unity is a PID.
This is
That
also
result, why? Can you give me an example?
Rx, Rx and Zx.
Very good. Rx and Zx. Can you tell me why Rx is a PID?
R is a field.
Yes.
That's why.
If it is a field, then what is the result? Can you tell me? Yes, you are correct. Absolutely correct. If R is a field, then Rx is a PID. That result is perfectly okay. But why Z is not a field and then why ZX is not a PID? What is the result?
Actually, x2. We should consider x2.
X?
2.
That ideal generated by x and 2. That is that is not a principal ideal in ZX.
Yes.
Actually, every principal ideal must be generated by only one single element. In x2, x2 means I am referring dots elements which are generated by x and 2. This element can't be generated by a single element. So that's
Very good. So he is saying x comma 2 in ZX. Okay, can somebody be tell me what is the speciality of this polynomial? So ZX mean a polynomial with coefficient from Z. Can somebody tell me what is the speciality of this ideal generated by x and 2 in ZX?
All such polynomials whose constant term is even.
Exactly. Very good. So you can write it. So it's a, if you consider this to be R, and in my last class, I have mentioned you how it looks like. So this is a commutative ring with one, and this is generated by two elements. How they look like? They should look like, say, RA plus SB, such that R and S, they are from the ring R, right? So for the, that is the general definition. Now if you consider here this x comma 2, then it should looks like all this R come from ZX, that means some polynomial fx into x, plus this s will also come from ZX, that means some gx into 2, such that fx and gx, they come from the polynomial ring ZX. Okay. Now you can understand that if I multiply x with any polynomial, then this product term will not contain any constant term. For example, suppose if you write it a0 plus a1x, something like this, and then if I am going to multiply with x, the constant term will be multiplied with x. As a result, in this product term, you will not have any constant term. Now here in G, you will have some constant term. You may or may not have. If you don't have, then 0 will be the constant term. If you have any constant term, then you are going to multiply it with 2. That means it actually looks like a polynomial whose coefficient is even, constant coefficient. And here there is no constant term. That means ultimately it looks like all such polynomial fx belongs to zx, such that the constant term of fx is even. Okay. Yes. So this is not generated. You cannot generate this by a single element. You cannot have a single polynomial which will generate this. You cannot have. That is why this is not a PID, but Rx Rx is a PID. Anyway, we will come to some more stronger result that will show us that this result is not correct. Anyway, you have already given this answer, very good. And then what's about the last choice? If R is an integral domain which has finitely many ideals, then R is a field. Is this result true?
What about Z8?
Z?
8?
Z8.
Yeah.
Z8 is an integral domain which has finitely many ideas. Then R is a field. Exactly. So Z8 is an, if R is an integral domain, Z8 is not an integral domain.
Sorry. Yeah. Final integral domain is always a field.
So any finite integral domain is filled, but we can have an infinite integral domain with finitely many ideals.
Give me some example.
I am thinking that example.
Yes, that's quite interesting. You know this example, right? So what you are actually searching for, tell me.
An infinite integral domain which is not a field.
Yes. But it should also have finitely many ideals.
Z root 2, will it work? I'm not sure though. Z root 2.
So what is your guess? First of all, try to think. Will it be true or false? Okay, so if we recollect all the results, then 39(1) is true or false? 39(1) is it true or false?
False.
39(2),
False.
3, 3, just now you mentioned 3 is true or false?
False.
3 is also false. That's the, sometimes for multiple correct choice you will have some extra advantages. So all the 3 options are false and you have to choose the correct option. So what would be your conclusion?
Then it would be true.
So it would be true, and you are trying to find something which will give you a negative answer. Okay, so that's very important. So if you are actually dealing with competitive exams, then this information, so a lot of informations are sometimes already given at your question paper itself. So here, even if you are confident enough about 1, 2 and 3, then you don't need to calculate or don't need to give some counter example or no need to prove it for competitive exams that the 4 must be true. That means what you are trying to do is not correct. It's basically you should give some proof of it. Okay, let us try to prove it. So it says that if R is an integral domain which has finitely many ideas, then R is a field. Let us try to prove this. So the proof technique would be like this. you may use many techniques maybe. So what is there? So it's your R is an, what is there? R is a integral domain. So R is an integral domain and it has finitely many ideals. So let us take any element A, some non-zero element belongs to R. Okay. So if you don't have any other element other than, so that would be a zero. So there must be some non-zero element within R. Otherwise, it could be a zero ring. And consider the ideal generated by A. Suddenly, this will not be a zero. Sorry, this will not be a zero ideal of R. Okay. Okay. Let's consider A square, A cube, and so on. Can you be able to go infinitely having all these values distinct? I mean, all these ideas distinct? Can you go forever such that all the ideals will be distinct? I have given you enough hints. Is the hints clear to all of you? I consider a non-zero element A and I start on making ideals generated by A, generated by A square, generated by A cube, and so on. What I am claiming, not all these ideals will be distinct. If all of them are distinct, then what would be the conclusion? You have infinitely many ideals, but it says that it has finitely many ideals. That means after some time, suddenly you will have to repeat. For example, say at some time n plus k, again you have to repeat with somebody. So that's same as say an, because not all of them will be distinct. What does it mean formally? That means that it will suddenly come back. That means they are not distinct, means there must be at least some pair which are equal. Now I think I have given you enough hints. So what you are actually trying to prove to show that this is a field, what is our aim? I have taken a non-zero element. What I am going to show actually? What is our aim? To show that R is a field? Tell me.
So R is finite.
R is finite. If you can prove that R is finite, then also it's done. But that would be, I think, will be very optimistic to show that.
Maybe only ideal, all the trivial ones.
So what you are
That
going to show that, I mean, you are all thinking too much. So what you need to show that R is a field. That means I have taken a non-zero element. What I need to show? I need to show that A inverse exists. That's all.
okay.
So this is an integral domain. All the properties are there. Only thing is that I need to show that any non-zero element should have an multiplicative inverse. That's all. I have taken this. So this is my aim. And what I am saying that if I have this kind of relation, then I am basically done. So that is your homework. So you need to check it. I'm not going to give you all the details. So this is your homework. So please check it and let me know. Okay. So see that all the problems that usually came, so they are now, so I think that is done. So this is the fourth was the answer here. And now very quickly come to here. This came in also December 2019. So now you can see that every year you will have similar kind of problem from this particular part. So here, what is that? I is an ideal object. Then which of the following statements are true or false? I mean, maybe multiple correct. Okay. So tell me, I is a principal ideal. Is it true?
True.
True. Because?
There is a
Because?
PID.
Yes, because Z is a PID. I is a prime ideal of Z. Is it true?
False.
False. Why?
Four. Generated
For
by
Z.
four.
Yes, very good. I is a prime ideal of Z, then I is a maximal ideal of Z. True or false?
False.
Why?
Zero.
Zero
Zero.
ideal. Very
Zero.
good. Zero ideal. If you consider I to be a zero ideal, then this is a prime ideal. Many of the students, they miss this point. Always they find that this is a PID, so every prime and maximal they coincide, but they miss the zero ideal. So that's the problem of competitive exam. You know the results very well, but when you are in under time pressure, many of the students they commit mistakes, and that's very common. So you have to be very careful while reading the statements. That's why I try to mention the points or the mention the areas where usually the students they get they do mistakes. Okay, so last one, if I is a maximal ideal, then I is a prime ideal. Is this
True.
result true?
True.
Yes, very good.
True.
So now you can see that all the similar kind of problems could be asked many places. If you go to the NBHM site as well, there also you'll find lots of problem. So in my problem set, I have also mentioned many of such problems. So please do that. And I'm sure that if you do this, you will get few of them, not maybe the exact problem, but the result must be useful for your any competitive exams. Okay. So I think I must stop here. So any question or comments for today? If you have, you can ask me.